Hello. Well, at last I can get on to something other than tacking with Woodstock. About a couple of years ago, I started doing some research on solar panels because we're going to need solar panels on the boat to charge the batteries all the time. And I bought some panels like this from Amazon. I'll just show you one of them. They cost about 10 quid each, and they are rated at 3.5 watts, 6 volts. The thing with solar panels is that you need to adjust the load on them in order to extract the maximum power from the panel. For example, if you left the panel open circuit, you'd get the maximum voltage but no current and thus no power. At the other extreme, if you short-circuited the panel, you'd get the maximum current but no voltage and hence no power. So somewhere between those two extremes there is an optimal value of load on the panel that will deliver the maximum power from the panel. Unfortunately, that optimal value varies depending upon how much light is falling on the panel. So I've been doing some research on that, and this video is about what I've been up to. This graph shows the panel voltage along the horizontal axis and the delivered power on the vertical axis, and you can see clearly that the power peaks somewhere between 4 and 5 volts at a value of about 1.9 watts. I made these measurements in full sunlight in April 2017, and the my camera exposure meter gave an EV value of 15.4. That's about the most power I've ever managed to get out of this panel. Although it is advertised as a 3.5 watt panel, it seems that you need a very intense perhaps a Saharan sun to get the power above 2 watts. I also measured the power under other sunlight conditions. The magenta line, this gives the power at EV 13.6, and the orange line at EV 11.9. The 11.9 sort of corresponds to a rather overcast day. You see, of course, that as the sunlight reduces, we get enormously much less power out of the thing, but also you could say that the optimal voltage is different according to the intensity of the sunlight. So you might say that the peak power comes at 4.5 volts here, and here maybe at 5.2 volts. So it's clear that if you wanted to extract maximum power from this panel, you'd need to adjust the load according to the amount of sunlight that was falling on the panel at that moment. Well, I did those tests using multimeters by hand, and it was not very convenient. So I thought it would be useful to have an automated way of testing solar panels. One of the problems with solar panels is that even if you go to a sort of professional website like RS Components or Farnell and look at solar panels, they're not properly specified. A physicist would like to know that if a panel is illuminated with so many lux, how much power does it produce? But nobody bothers to tell you that, and actually we need to know. So, and another thing that's concerning me is that you can look up on tables which purport to say, you know, how much energy you'd get in Britain over a year from solar illuminance. I'm not sure how reliable that information is, and in any case I can't relate it to the particular solar panels that I've got. So for both of these reasons I thought I would start a long-term test of these solar panels, monitoring the amount of power that they produce and what the optimal load is on them all the time. Well, I've got one of my eBay solar panels here, and I've connected some 0.5 millimetre square copper wire to it, which will be okay so long as it's very short. And I've just got a piece of acrylic here, which was the first thing that came to hand, which I've sanded a bit. What I'm going to do is I'm going to put this on top of that like that and stick it down with a marine sealant, and then I'm going to put it on a long-term test. Meanwhile, I've cleaned it with this. Do you think that would do? So if I turn this over and squash it down in the middle here, everything's going to be wonderful, isn't it? I wonder what that looks like underneath. Well, not that brilliant, is it? I should have put a bit more on, shouldn't I? I think we'll just leave it there and maybe put something heavy on it. Alright, so we'll just leave that there for 24 hours. So I've knocked up this platform onto which to put the solar panel with a bracket there, and then I'm going to mount that up there, which is about the only place I can find which isn't overlooked by trees in my garden. Right, so there we have it. Some gaps. So I wonder how much this weighs now. 234 grams, whereas a bare one is 80 grams. So just putting this piece of acrylic and all this sealant has more than doubled the weight, which is worth knowing, isn't it? We'll have to think of a better way of sealing this. It's got to be sealed. Right. Well, I fixed this waterproof solar panel onto the top of this bracket, and I put some stainless steel bird spikes on it. The plus side of these is it should stop pigeons from crapping on the thing and from sitting on it and upsetting the readings. The minus side is that there will be cast a very small shadow on the panel anyway, but no more than will be cast by the sails if the panel is on a boat. So I think that's fair enough. So now I'm going to put it up on my wall. I should explain that these red and blue wires are quite adequate if one was going to connect this panel by a short wire to whatever it's driving. But as I'm actually going to connect it with quite a long wire, I decided rather late in the day to use these rather thicker black wires in order to avoid a volts drop when the current is about 0.5 amp. So by the time the signal gets from there down to the other end of this wire, it should be about the same, given that this black wire is only 0.0095 ohms per meter, which I've measured or calculated or something. Right, well I suppose I should have looked up here before I started drilling that hole from outside, but we'll see what's up here. Fortunately we have plenty of light up here, which is more than can be said for most attics. I just have to be careful where I put my feet, because otherwise I shall just go straight through. And actually that's the wrong way. I should be over here. Bloody hell, there's a light over there but the bulb has gone. Now isn't that typical? The one bulb that I need to work is not working. I'll go downstairs and get another bulb. So I put a new bulb in. We should be coming through somewhere. Maybe I shouldn't have done it in the middle. Maybe it's that piece of wood that I'm cutting through. I don't know. I have to get closer than this. There's a power shower down there which I started installing about 10 years ago and never finished. Yes, well, it's coming through there. Which will be fine, because I can just bend the cable around here. I'm certainly not going to drill a hole in this piece of wood, which is structural and holding up the it's part of the truss. And as everyone knows, you can't trust trusses. So we'll leave that truss alone. That's absolutely fine. We'll just poke the wire through there. Right, so up in the attic, see if I can get hold of it from that side. And if I'd had any sense at all, if I'd just put it there or here, I wouldn't have hit that bloody piece of wood. Well, this was easier to do 20 years ago. Isn't quite so comfortable nowadays. Well, it's up. You would not believe the number of tools and operations I've had to use just in order to do this simple thing. Simple thing that you would have thought would take half an hour has actually taken me on and off a couple of days. But anyway, it's up there with the television aerial. So I've been developing over the last week or so a test circuit to be put up in the attic to control the solar panel. It's down there at the moment, and it has whoops, I blue tacked that on. It's got a power MOSFET here. So to explain how this circuit works, we've got the solar panel here, and connected across it there is an N-channel enhancement mode MOSFET and a 1 ohm resistor. So by turning this MOSFET off, I can open circuit the solar panel, and by turning it full on I can virtually short circuit the solar panel. This op-amp multiplies the voltage across the 1 ohm resistor by 5.7 so that it can be conveniently sensed by the micromite analog to digital converter. So this circuit here is effectively measuring the current produced by the solar panel. And this op-amp up here is just a buffer which measures the solar panel voltage and scales it down to a value that the micromite can read. So the micromite program can read both the current and the voltage that the solar panel is producing. This bit of the circuit here controls the MOSFET. The micromite does not have a D to A converter, so I can't output a defined analog voltage from the micromite, but what I can do is output a pulse width modulated signal, and I can change the mark space ratio of that. So what I'm doing is taking the PWM signal and just smoothing it with this RC network and putting it into this op-amp, where it compares it with the measure of the current flowing through the 1 ohm resistor and applies the difference signal to the gate, turning the MOSFET on or off as necessary in order to bring the current to whatever value is specified by the PWM signal. So in other words, the Micromite program can, by changing this signal here, determine the load on the solar panel. Now, as soon as I drew this circuit, I realized it was going to fizz, by which I mean it's going to oscillate at high frequencies. The reason for this is there's a loop here which is enormously high gain. There's gain in the MOSFET, there's a 5.7 times gain in this op-amp, and there's a 40,000 times gain in this op-amp. So certainly it is going to oscillate at some frequency, and in fact it turned out it oscillated about 1 megahertz. So I added these other components, which essentially just put the kibosh on the high frequency gain of this circuit, allowing it to operate at low frequencies but stopping it oscillating at high frequencies. So this is the circuit that I'm going to put up in the loft, and then the Micromite will send a serial signal down to a computer down in my study. This scope trace shows some of the voltages in the circuit. The dark blue trace is the control signal from the Micromite determining the load on the solar panel. The magenta trace is the proportional to the current through the solar panel. The cyan trace is the voltage on the gate of the power MOSFET, and the yellow trace is the solar panel voltage. So the Micromite software begins by open circuiting the solar panel and then short circuiting it. The Micromite then applies a gradually increasing load to the solar panel whilst monitoring the power output, and when it's got some idea of where the optimum load should be, it then applies a much shallower ramp in order to identify the exact optimal point, and it then sets that point. So I've got the solar panel leaning up against the window there, and the sun is up there, so it's a glancing angle like that onto it, and we get 539 milliwatts. If I go back and put it at a more direct angle like that, we will get a new reading, nearly 1 watt. So I think that kink in the graph is caused by my moving it. Let's just see if we get a better figure next time. Yes, that looks more better. That looks better. So that's just the effect of sine theta. Sine 90 is 1. Sine whatever is a half. So I'm visualizing what's coming out of the Micromite in this browser window, and let me just, that's a more sensible one. So we got a measure of the power output, 641 milliwatts, and it tells me what the optimum voltage is in order to get that power output, 4.59, which is here. This is a plot of power output against voltage, so we need to choose the peak of that. And this red line is just the current, which of course goes to its minimum when the panel is open circuit, and is at maximum when the panel is short circuited. I'm also calculating how much power I would get if I just fixed the panel voltage at an arbitrary value, which I've chosen as 5 volts at the moment. So the optimum voltage in this particular case is 4.59 when we get 641 milliwatts, but if I were to fix it at 5 volts, it would be 573 milliwatts, which is 10% down. this is one of the things I want to assess, is what is the optimum voltage to choose for this solar panel, assuming that we don't dynamically optimize it all the time. Because we've got 9 panels, all of which are illuminated in a different way, with the sails shading some of them and others, it would be a bit complicated optimizing each panel separately. But so I'm shooting, hopefully, for fixing the panel voltage at a reasonable compromise. So it does this whole thing once every 10 seconds or so, and I can just flip through the different ones to see what's going on. And it plots a graph here of power output against time. So this bottom graph shows what happened when I went to lunch about 12 o'clock in full sun, and came back about 4:30 after walking the dog, and the sun had got considerably less bright, and as you can see, the graph started out about 500 milliwatts and deteriorated down to 28 milliwatts at the end. The 2 little blips at the left-hand end are the occasion when I turn the panel directly towards the sun, just to demonstrate it, as you saw in the earlier video. So that's the start of the long-term solar panel test, and I'm going to perhaps leave it up there for a year. We might actually have to do something useful with the data before the year is out, but I must apologise to my less technical viewers that this has been perhaps a too technical video, but there you go. Some of these things are technical. Anyway, thanks very much for watching.